Pacific graduate residents. So this event is part of a long-running lecture series sponsored by the MIT Presidential Fellowship Program and run by the Sidney Pacific Committee on Scholarly Interactions, also known as CoSI. So today we're honored to have Professor Sara Seager. Professor Seager earned her PhD from Harvard and is now a professor of planetary science and physics at MIT. She has been a pioneer in the vast and unknown world of exoplanets. Dubbed an astronomical Indiana Jones, she's on the quest after the field's holy grail, the discovery of a true Earth twin. Among Professor Seager's list of awards, she was the recipient of a prestigious MacArthur Fellowship last year, also known as the Genius Grant. So let us welcome Professor Seager, who will tell us about the exciting world of exoplanets.
Hi everyone, can you hear me? Yeah. I'm just going to set the microphone up. So I'd like to know how many of you in this audience have heard about exoplanets. I wasn't sure if you were going to be a self-selected group or a sort of random sample of MIT students. Well, I'm here to tell you what's going on in exoplanets as well as what's happening here at MIT. How many of you believe there's life out there somewhere? And how many of you believe that that life has visited us here? Okay, we do. I just thought I'd throw that out there. We can get to that. I'm actually having a little trouble with this microphone. I think I might just use this. I don't know if it's actually even working. Oh. Well, I'd like to prefer to use this, but it's... All right. Is the microphone on? Can't tell from here. Okay, great. Well, the other thing is my talk is a Prezi talk. Have you guys heard of Prezi? Yeah? I guess the sort of younger crowd knows what it is. I was lucky because the Prezi folks actually made my talk for me. They wanted more people at MIT to use it, and so I'm partly here to, I guess I'm partly here to promote Prezi because they made my talk. So right here you see in a picture of a dark sky. Have you guys been to a dark sky? I really hope all of you who haven't have a chance to see it someday. I'll never forget when I first saw a dark sky. I think I was about 10 years old. And it was the first and last camping trip that my dad ever took me on. Subsequently, I went on more trips myself, but I just remember walking outside in the middle of the night, outside of my tent, and I just looked up. I just had no idea there could be so many stars. There's just so many of them. It just was like shocking. And so I guess for me, seed was planted early about the stars and the cosmos and whatever's out there. And now whenever I look at the stars, even if it's just sometimes here you can see stars, even from Cambridge, even from my office. I have an office in Building 54, one of the highest levels, overlooking the Charles River. Even on a clear night, sometimes we can see Orion, the constellation. You only see a couple of stars, but still, when I look at those stars, I wonder if there's anyone orbiting the planet on those stars, you know, looking back here at our star and wondering if there's life here. Okay, well, I'm going to start out quite basically, just so we're all on the same page in case there's anyone who either forgot or wasn't thinking about it lately. I think we actually have some interference here with the other microphone, maybe? Yeah, that one's off. We're having some technical difficulties. We always joke around that if we can't figure these technical difficulties out, we won't be able to build a big space telescope to find the other Earths. But okay, so every star in the sky is the sun. And if our sun has planets, we would naturally expect other stars to have planets also. And they do. And astronomers have found that every star in our Milky Way galaxy, and that's out of 100 billion stars, should have at least one planet. And in fact, most of them probably have many, many more planets. So the thing that we found was, well, here's a picture of our solar system, just to give us a bit of a reminder of some of the planets. We have the sun is shown in the middle, with Mercury, Venus, Earth, Mars, Jupiter, and then the other planets are further out. This green zone here represents the so-called habitable zone, or Goldilocks zone, where a planet like Earth with a thin atmosphere is largely heated by the sun. It's also controlled by the greenhouse gases in Earth's atmosphere. But it's largely heated from the outside. We call it the distance from the star, where the surface of the planet is not too hot, not too cold, but just right for life. And so what's so interesting to me, though, is that out of all the planetary systems that we found, we actually have seen nothing like our solar system. So in our solar system, people had theories about how planets form. And it was very neat where the terrestrial rocky planets are quite close to the sun, and the giant planets like Jupiter, Saturn, Uranus, and Neptune are far from the sun. And it's an example of the scientific theory that just had one example. And so it's not always great to build a whole theory around one example. When we found all these other systems, none of them are like our solar system, such that we think less than 10% of sun-like stars would have a system like our own. We don't know the answer. All we know is that we found all the systems that are easy to find. It's quite hard to find one like our solar system for just selection effect reasons for discovery techniques. Okay, well, I'm going to show you actually a movie of one of the new multiple planet systems. This is a system showing you the so-called habitable zone in green here. And this particular one has 1, 2, 3, 4 inner planets. And this fifth one that's in the habitable zone, but it's probably too big to be a habitable planet. It's just a cartoon. It was in a big news announcement from a couple weeks ago where the Kepler Space Telescope revealed 700 new exoplanets. I hope you can see it okay. It's kind of, can you guys see the white? It doesn't totally matter, but it's just showing you the relative motion based on Kepler's laws of these planets. Their periods and the separations from the star are known. And it's zooming in to show you a view edge-on, a special configuration when planets transit the star, that is, they go in front of the star as seen from the telescope. And this particular star has the planets all quite tight in a plane, all of them orbiting the star. And this is just showing you their relative sizes. We can't spatially resolve the star like that. All the stars are just point sources. But this is a cartoon of what that particular system looks like. But guess what? We know of so many multiple planet systems, it is truly awesome. Somebody, a professor from Chicago named Dan Fabricki, he made this. It's called the, I'm going to try to put the sound on, hopefully we'll. It's all to scale here. You can see the solar system in the top left is quite boring compared to the other ones, where the sizes of the circles represent the size of the planet. You see there's all sorts of systems. You're supposed to see from this image that all kinds of planetary systems exist. You're just seeing the cartoon version of what's probably tens of thousands of people hours of work in looking at the data, finding the planets, and actually, at the end, making this kind of cartoon. This one looks cute. Look at that one. All right, well, that was like a picturesque intro. So, actually, okay, I do have some movies. It's really just for entertainment, but I want you to know there's a lot of real science behind this. So Kepler has found, the Kepler Space Telescope, it was launched on early March 2009, and it operated for 4 years before it stopped working. There are reaction wheels. There's 4 of them. You need 3, one on each axis, to control its pointing, and actually 2 of them failed. There's kind of a story behind Kepler, which I guess I'll just tell you briefly, because it's sort of good to know about it for experimental purposes. The real goal of Kepler was to assess how common are Earth-sized planets in Earth-like orbits about sun-like stars. How common are they? It's like a census of exoplanets. And Kepler needed 4 years, essentially, because think about it, our Earth goes around our sun once a year. That's how we define our year. If it's transiting, that is going in front of the star and seen from the telescope, you'd like to see it go around twice. Well, you need it to go around twice so you have a period. You'd like it to go around a 3rd time to confirm it. Okay, so you're looking for a drop in brightness when the planet goes in front of the star. You want to see it twice, and then you'll know what your year is, because you want to find a planet with a 1-year orbit, and then a 3rd time to confirm. That would be 3 years, right? To find a planet with a 1-year period, you need to see it 3 times, so it's 3 years. And you can't guarantee that that first transit will show up right the first day you look, right? So you wanted 4 years. So something kind of bad happened, because Kepler lasted for 4 years, but it's sort of like, you may or may not have this experience, but if you buy an appliance, like a washing machine, and it's guaranteed for 4 years, but then it breaks like the day after. It's unfortunately a bit like that. And it only had to last for 4 years. Typically, spacecraft lasts much longer because everybody holds margin. Everybody makes sure that their subsystem or their parts really could last a little longer. But a funny thing happened, and that is the stars like our sun that we were looking around with Kepler, it turns out they were a little noisier than our sun. That is, they vary a little variability from star spots and other things, such that we couldn't find the signal we were looking for. We'd actually need more data because it was what we call white noise. You just need to get twice as much data to find the same signal we were looking for based on how noisy it was. And so it was a bit unfortunate. The joke in the team was our sun is not a sun-like star. Because we thought all stars like the sun are truly like the sun, but until the Kepler Space Telescope went up and could measure stars with their brightness at very, very precise levels, we didn't have any way of knowing what stars were like in terms of their average brightness. But it wasn't very funny after the Kepler Space Telescope malfunctioned, just at the time when people had realized you need another 4 years of data. But the cool thing is with the Space Telescope is nobody wants to see one go to waste, and so engineers have figured out a way to use it, not for a slightly different purpose. But they decided that they could use solar radiation pressure. Photons cause pressure, but just a tiny amount, to help stabilize the telescope. So they'll use solar pressure for one axis, and the two remaining reaction wheels will control the other two axes. Now this way they can only look at one field for 80 days because of its orbit around the spacecraft itself is orbiting the sun, and so it has to change. So instead of Kepler finding the true answer that we really wanted, we wanted to know how common are Earth-sized planets and Earth-like orbits around sun-like stars. It found a whole bunch of other things we hadn't actually anticipated. Kepler could perform at a factor of about 100 times better than anything like it ever before. So think about your own field of research. If you or one of your friends or colleagues or professors develops a new tool that works at 2 orders of magnitude better than what you currently have, in many fields you'll open up a whole new universe. So one of the cool things Kepler found, it's all in animation form here. I thought, and this is showing you what we call a hot super-Earth, a planet that's more massive than Earth, a bit bigger, but rocky. This was the first rocky planet we ever knew about. This animation is showing you what it would be like if we could fly to this planet. It's so close to the star, its year is actually 0.85 days. That means instead of taking a year to go around, it takes just a tiny short time, less than a day. And this is showing you an artist's conception of a planet. That the planet is so hot, heated by the star, that it's hot enough on the surface to melt rock. So that's quite hot. That's like 1,500, 2,000 Kelvin. And this is showing you a comet-like tail, like if the wind is ablating the surface of this planet. And by the way, this is one of the fun parts of my job, is I get to consult with artists to make the models that I make into art. And the artist is showing you that this planet, we expect it to have liquid, not from volcanoes, not lava from volcanoes, but just lava from its sun, its star, heating it so intensely. Now you see the artist's conception. Artists can have fun here, showing you as if we could go there. But I would have some kind of tenuous atmosphere, but perhaps not a really big one. This was the first confirmed rocky planet based on its size and mass and hence average density. It just has the name Kepler 10b. People often want to know where do the planet names come from. There's a big argument in the community about this. People want to name it after their favorite thing, but it doesn't work that way, unfortunately. There's I thought we should sell the names and try to make some money initially, just like, the asteroids get named quite easily. When I was actually a grad student at Harvard. I don't know if that's a bad thing around here. People like to complain about Harvard, but I worked at this place called the Center for Astrophysics, where they had the Minor Planet Center. If there was a new asteroid or a small body found, it got called into that center. And they could also then name asteroids. And sometimes it was like if someone, it wasn't this easy, but if someone retired, they got an asteroid named after them. So I sort of thought we should do the same thing with planets. There's so many of them. But it turns out Kepler is just named after the Kepler found. If the star already has a name, the planet gets a letter, like Ursa Majoris, little b, ECDE, named in the order of discovery. In case of the Kepler stars, they were never named because there's so many stars that are faint that people never really cared about. They weren't cataloged like our nearby bright stars were. So they get the name Kepler, and then Kepler would give it a KOI number, Kepler object of interest, and then when it finds a planet, it gets a Kepler number. So it's all just like a catalog based on the order of discovery. So that's Kepler 10b, and many more have been found like it. I just chose a few examples to tell you about exoplanets. And now I get actually to probably my favorite example, and that is the so-called mini-Neptunes or sub-Neptunes. Here's an image of Earth, an Apollo image of Earth, and there's another, I believe it's probably a Hubble Space Telescope image of Neptune on the right. And in between is just a circle, a white planet, about so-called planets mini-Neptunes or sub-Neptunes. These are planets that are 2 to 3 times the size of Earth. We have nothing like it in our own solar system, where Neptune and Uranus are about 4 times Earth. And the interesting things about these planets is we actually have absolutely no idea how they formed. In our own solar system, we thought we understood how our planets formed. That is, Jupiter and other planets like it accreted material, icy and rocky material. It started growing until it reached about a 10 Earth mass core, such that its gravitational pull was strong enough to suck in all the material around it, like a planet feeding zone. Jupiter essentially, we think, sucked out all the material all around it that its gravitational influence could reach and kept growing until it finished that and could grow no longer. So it got to be about 10 Earth masses and went into a runaway phase and just kept growing. And planetary scientists believe that's the basic story of planet formation for giant planets. And our own Uranus and Neptune, we didn't totally understand, but had some contrived theories like where Uranus and Neptune are, there's not too much material, it takes a long time for a planet to form, and perhaps a lot of it just dissipated before they could really form. But now all of a sudden we're confronted with these mini Neptunes. They're basically, we don't totally know why they have this stunted growth. We know they must have a lot of hydrogen helium, more than could be outgassed from a rocky type of planet, and it's quite a big puzzle. This is what I would work on if I was a student today. A new problem that we have no idea. And you know why it's such an exciting problem? Because those so-called sub-Neptunes or mini-Neptunes, they are 10 times more common than Jupiter-sized planets. And we've seen this not just from the Kepler data, but from other sources as well. This is just, I probably should have put more charts in here for you and graphs, but this is sort of a takeoff on a public talk that I gave last week. So for the public, I would only have one graph because most of them won't follow it. But in this case, you can see here on planet size on the bottom and fraction of stars with planets. This is just for planets with less than 50-day periods, that's less than 50-day years, but there are other techniques show you the same answer, essentially. And what you can see here is it's giving you the cartoon picture of the different sizes. But here's Earth size, and this is the 2 to 3 times the size of Earth in this part here. So small planets are so much more common than Jupiter-sized planets. And for these gas objects especially, it's just a huge surprise. We don't know why that happened. So actually, if there's only one thing you remember about my talk, you could take home and maybe tell your neighbors or friends or colleagues, it's this, that these small planets, we have no idea what they are. They're actually the most common planet in our galaxy. Now we're hoping that smaller rocky planets are even more common, that there's even this one here, the error bar is too big for us to really say, but we're hoping that this won't skyrocket, because these are the rocky planets that will have a solid surface and they won't be too hot for life as we know it, and we're hoping that those ones are ultra, ultra common. Okay, so I do have this explanation of transit light curves. So look closely, would you see a planet? This planet's supposed to be about the size of Earth. You see it crossing the star? So we don't see that. We don't spatially resolve any other stars other than our sun. And this is showing you what happens. You measure brightness of the star as a function of time, and then you see a drop in brightness as the planet goes in front of the star. And then when the planet comes back across, you'll see this go back up. And they've added noise here, which is cool, right, for a cartoon, added noise. Now, this signal here is what the Kepler Space Telescope looked at a field of 150,000 stars for 4 years. And the original PI of the mission called it the most boring mission ever, because all it did, every 6 seconds, it took the same picture of the same stars. And it would bin it into, because it couldn't downlink all that data, so bin it into bins of 1 minute for a subset of stars that the team could choose, or 30 minutes for most of them, and every quarter of a year would downlink that data to Earth. And so a lot of the data didn't come back, but a lot of it did. And then they would search for these. And you know the best way to search initially to understand your data? By eye. So you'd have people come to NASA Ames. You couldn't just send it around the world because of ITAR. They worried all spacecraft, unfortunately, are considered under the as like a terrorist weapon. It's a big problem here, actually, at MIT. But they, so you'd have to go there and look at it. And you really want to understand your data before you set a computer algorithm on it, because the human eye, like our brains just work so well at things like this. And then you do your algorithm, and in the end you can end up missing things, because what you put in is what you get out for computers. Yeah, so look at the data, because there can be some noise in the data that ends up looking like a transit, and you want to be able to discriminate among that. And there's other astrophysical false positives also. But that's the transit, and that's the technique that has been arguably the most successful today. So out of all those planets, and I just gave you like an overview of some of the highlights of the field of exoplanet research. But the most question that people have, out of the questions I get asked most often, is do we know of any habitable planets so far? Do we know of any planets in their so-called habitable zone that are the right distance from the star so that they could have liquid water at the surface? And what's really cool, actually, is there are a bunch of, you have to be careful how we word this here. They're potentially habitable planets. Here they're all in cartoon form. And this is just showing you, remember we talked about the names? Gliese is a catalog of small stars, typically, mostly small stars. And there's a bunch of them. Here's Tau Ceti. Some of these are controversial. Some of them are going to be too big to be habitable. But my point to you is that we don't have enough information to know if these planets are habitable. We have a mass in some cases, a size in another case. Sometimes we have a mass and a size. We get an average density. And on the whole, we don't have enough information. There actually is a website that actually shows these. It's called the Habitable Planet website or something, and we'll go into more detail. What I think is really super amazing about this is that, just in the last couple of years, our technology, that is our telescopes on the ground and in space, was actually good enough to even tell whether there were rocky planets and habitable zones of stars. And just the fact that when we first became able to do it, we saw at least a dozen planets here. It's really just the tip of the iceberg. So we were just barely able to see, and we saw. So there are many, many more out there. And it's actually my main job, which I'll get to, my main thing I'm doing, is how we're going to find and identify the so-called habitable worlds. One thing I wanted to tell you about these habitable planets, what makes it so hard to know whether they will be habitable, is the so-called greenhouse effect of their atmosphere. I actually see at least one of my students took one of my classes before. It was called global warming science. So working on exoplanets, it actually is related to Earth and other planets. And my main course I teach at the graduate level is actually called Radiation in the Atmosphere. And we go over radiative transfer and other physics that helps understand how light gets absorbed by molecules in our atmosphere and then what happens next. So greenhouse is a real problem on Earth, right? You hear about global warming and people are worried about parts per million of carbon dioxide. But imagine if our planet had double the carbon dioxide, or triple, or 100 times more. Our atmosphere would be much more of a greenhouse. And that's really our main problem for not understanding habitable zone planets. We don't know their atmospheres. We don't know why our Earth has the massive atmosphere it does, or the composition. We can kind of explain it, but not totally. Like most of our atmosphere is nitrogen, 80%. We don't totally know why. And so that's really one of our biggest challenges. So to respond to that challenge, I actually wrote this article last year. It was actually invited, you know what? Okay, unfortunately this version doesn't have it, so I'm gonna have to, what do you think? Well, if I have time, I'll come back and show it to you. I was expecting to show it to you, because I was gonna tell you a funny story about it. It was an invited review for science, and they want you to tie things together and be provocative. And we actually wrote about the habitable zone and how it should look. Not just that little ring, but in fact, because of all these different types of planets, our habitable zone is huge. There was some review material and some new material. The review material I thought you'd like, because it turns out that some more massive planets will be able to hold on to hydrogen gas. Our planet, we can't hold on to hydrogen, it's too light. The analogy is not totally right, but partially right. So you know if you have the helium balloon? I couldn't resist asking how many of you had the helium balloon and let go of it as a child, by mistake. I can't believe there's so few. Some people let go of it on purpose, but it's like the gases are so light and that it can't stay here, but some exoplanets will be massive enough or cold enough or both that they will retain hydrogen. And molecular hydrogen is a nasty greenhouse gas. If we had it here, we'd be much deeper trouble than we are. Hydrogen, it turns out that just trying to think of how much technical detail you're interested in, but it turns out it's a homonuclear molecule. You have two hydrogen atoms, and so it doesn't have a dipole moment. It's not able to interact with light the way like carbon dioxide or methane or other gases can. And so it doesn't have like discrete bands. If you know anything about spectroscopy, these other molecules have discrete bands where they rotate and vibrate and absorb. But molecular hydrogen, it gets collision-induced opacity. So other atoms and molecules collide with it and induce a dipole moment. And the end result is that instead of having discrete bands, it absorbs continuously across the whole spectrum if the pressure's high enough. So it's this potent greenhouse gas because it absorbs essentially at all wavelengths. And not only that, unlike carbon dioxide, which freezes out, Mars is not habitable because the carbon dioxide is frozen out and there's very little greenhouse. Actually, not all the carbon dioxide is frozen out. Past Mars, carbon dioxide will all freeze out. But for hydrogen, it doesn't freeze out until something like 70 Kelvin. You'd be a planet very far away. So far away, some people have proposed that you could have rogue planets, planets that are kicked out of their solar system dynamically, that don't have a host star, that are still habitable. If they had the right amount of hydrogen and they still have radioactive decay on the inside that kind of comes out as heat, that heat could still be trapped in the greenhouse. So we have that, and then we have the inner edge of the habitable zone. This is what people got upset about. One of my postdocs, András Szám, worked on a paper. Other people have done it also, but we like to think he did it more exhaustively. And the question is, in our planet, water vapor is our biggest greenhouse gas. And water vapor, we have a problem because we think that if our planet gets too hot, we'll have a runaway greenhouse where water absorbs light. But then if our oceans evaporate, our water will fill our upper atmosphere where sunlight will break apart the water molecules and hydrogen will escape to space and eventually it will run away. So if we imagine our exact Earth much closer to our sun, our water would get boiled off. But then the concept is, well, what if we had less water vapor? We'd be less susceptible to the runaway greenhouse for the same distance from the sun. And so the concept was you could have a lot less water. And as long as you had the kind of right amount of water, you could have habitable planets much closer to the sun. I don't know how many of you got that story, but the point I wanted to tell you was just that little kind of thought. It set up like a fire in the community. And people got very angry and upset. And people started arguing, you can't have this. And the thought was that on our Earth, the thought was that when you sort of have all or nothing, that when your planet forms, it's born with a certain amount of material, and that's a lot of it outgasses. You can't just have a tiny amount of water. You either get a lot of water coming to your planet because it gets delivered by comets or asteroids or both, and then it comes out, or you just had really none, and there was nothing to really emerge. Anyway, whatever the arguments are, it got people unhappy. But the reality is we don't know, and so we decided we'll let it wait until we have observations in the future, and we'll see if there are planets with water vapor much closer to the star than our own Earth is. So now I'll get to the second part of my talk, which is how do we find and identify habitable worlds. We have two ways to do it. I think I already alluded to the fact we need to see the atmosphere. We need to know the greenhouse effect, and we also hope to find signs of life on these planets, which I'll get to towards the end of my talk. So the first way we want to do it is, I call it the Earth cousin way. Like ultimately we all want to find the Earth twin, but it's so hard to find an Earth twin that our first thing is to step back and look for big Earths orbiting small stars, because these are easier to find in today's technology. So for the big Earth orbiting the small star, they transit the star, go in front of the star as seen from Earth, or from the telescope. And what we'll do is we'll measure the size of the planet. So what we're going to do is we want to find the planets and look for their atmosphere. But the way we can see their atmosphere is see in the cartoon picture, the blue part of the planet, it's supposed to represent the atmosphere. It's quite exaggerated in terms of size. And that light from the star it can pass through the atmosphere, just like shining a flashlight through a fog. And some of the light doesn't make it through. Parts of the starlight won't make it through. And from that we can tell wavelength by wavelength what gases are in the planet atmosphere. And that actually is really, really cool. We could have done that for a handful of planets. When the planet goes behind the star, we see the planet light disappear and then reappear. And all of this, again, we're not seeing the star spatially resolved. We just see a point of light, but that point of light is changing in time, just like that light reflection. So actually, we can do a lot with these so-called transiting planets. And for a big planet transiting a small star, it all works out for us. So this is established techniques by now. And so now I'm pleased to tell you about TESS, Transiting Exoplanet Survey Satellite. This is an MIT-led NASA mission. Have any of you actually heard of this, TESS? The plan is that we're going to send TESS up and find a lot of short-period rocky planets transiting small stars. And then we're going to follow up their atmospheres with a space telescope called the James Webb Space Telescope that's being built now. It's supposed to launch in 2018. And we'll observe that. Now what TESS is, you can look at it. It's actually a $200 million NASA mission. If we had time, I could give you a tutorial on cost and then NASA cost. Like it's sort of funny but true in a way, because it's like you budget something to do, like a renovation, or you're going to do a project that involves buying something. It always ends up costing more. And actually there's a formula that proves why it always costs more, for every project. It's the same amount. It's quite expensive. Even, it's just an expensive project. Even with TESS, there's essentially no new technology and only one deployable, which are these solar panels. What these are essentially, I call them glorified telephoto lenses. And there's 4 of them. And they're actually being designed and built at Lincoln Lab. They're very special. They're athermal, so they're not supposed to heat up. They're all supposed to not supposed to change temperature in ways different from different parts of the lens assembly. The detectors are being made at Lincoln Lab, and the electronics are being made here at MIT, and the whole camera, that is the telescope lens and the baffle and the detector and the electronics will all be assembled here at MIT in Building 37. And these are about 100 millimeters in size. Each of them has a 24 by 24 square degree field of view. They're all on the same platform. And I hope you can get from this, they're trying to see a wide swath of the sky at one time. And this is just, they've got these ginormous baffles on them to block out light from the sun and moon. And then here's another kind of protector baffle-like structure. This whole thing is about the size of a giant washing machine, so it's like about this tall. And there's actually a mock-up model made that's over in Building 37. It's got a dish somewhere on it. And TESS is going to go into a orbit where it's a 13.6-day elliptical orbit. So it'll spend 3 hours near Earth, zipping by, and then it goes far away from Earth, because Earth is kind of bad for exoplanets. It's bright and it's hot. And in low Earth orbit, you'll be heating up and cooling down. Going to low Earth orbit, like where the Hubble Space Telescope is, it's a 90-minute orbit, and you're constantly going into night and day, heating up, cooling down. It's not great. So there's this really cool new orbit. That's where TESS will be. TESS is going to launch in 2017. If you have any more questions during Q&A, ask me about TESS, because TESS is going to be great. And it's going to be the biggest thing in exoplanets when it launches, and that's great for us here at MIT. It's led by George Ricker. He's the PI. Okay, right, so I could have launched into like details about all my computer models of applied physics. We make most of our models from scratch. We don't usually use commercial software because we have very specific things we need to do. It tends to be time consuming, but as a student, like you'll actually understand it better. But instead of telling you about that, I'll just take you on a virtual trip to one of these so-called habitable worlds, the big Earths transiting small stars. Now, a small star has a lower luminosity output than our sun. Our sun is a bigger star. And so that so-called habitable zone is much closer to the star than the Earth is to the sun. Instead of a 1 year period, that time it takes this planet to go around the star would be anywhere from like 10 days to 50 days. So your year would be actually quite short. Now for planets that close to the star, they get what we call tidally locked. That is, their lowest energy state, unless they get trapped in a resonance, is they show the same face to the star at all times. So think about that for a second. That means that every time they go around, they rotate once. That's like our moon actually does that. You know when you always see the same face of the moon? I mean, it's not perfectly always, but it's close enough. Because you actually can see more than a hemisphere by a little bit. But think about that. Every time our moon goes around, it's just rotating so that it only goes around. It's cool, right? These planets do that also. And do you know about what that would mean if you were on a planet, if we could actually go to that planet? We just described what it would be like if we were on Earth and we see the moon, or if we're on the sun and we see the planet. What would it be like? The sun actually would always be in the same part of the sky at all times. So that is kind of cool, right? You could go to that planet and go where the sun was always setting. That's why I showed this picture. Or, you know, if you're the astronomer, you want to go where it's always night. Or maybe you want to go where it's always day. It's cool. And this sun would be quite big in the sky. In this artist's conception, they've also shown you another planet that happens to be going in front of the star. And here's another planet too. Looks like the moon. The artist did an artist license. They always do, right? But they have to show the sky is very red. Yeah, so it would be cool. This would be in the same spot at all times. And the other thing is the year would be very short. So for kids, I didn't expect any kids in the audience, but I did see one little kid who's too little to get why this is cool. And the mom's probably a little too young to know why it's cool, but the kid would have their birthday like every 10 days. So for the mom, that's a problem because you have to do the party and stuff. Well, I'm sure they have a different system, right? And the thing for astronomers is, people are always making a big discovery at the wrong time of year. You usually make a discovery for whatever reason, just when you're about not to see that constellation. We say it goes behind the sun, but as you know, our Earth goes around the sun, a different part of the sky is in view at night. And it's always a problem. You wouldn't have that problem because every 10 days you're kind of completing your orbit around your star. But on second thought, these planets might not be very good. Because these so-called M stars, they give off more flares than our sun. They tend to be more active, more variable. And they might be spitting out a bunch of, you know how the ultraviolet's like bad for your skin? They may be throwing it worse than that, things that can mutate. We're not really sure actually if these are good locations for life. I mean, presumably life could live on the dark side or subsurface and not have a problem. But it certainly wouldn't be a good place like for your cell phone or for satellites and things like that because the stars are really just too active. And sort of on a more serious level where there's some kind of concern. We don't like to talk about our concerns out loud because we're so optimistic, but that if the star is so variable, it's going to interfere with our observations of the atmosphere. For many of these planets, we need to look at a spectrum, right? And I talked to you about that in the cartoon. Where that atmosphere, this is really exaggerated. That, if you were to do the calculation here, if we were allowed to assign homework, you'd see that atmosphere is very thin compared to the size of the whole star. So you're essentially looking for your signal as the size of the annulus, the area of that annulus of that atmosphere compared to the whole star. It's very small. So we'll probably have to see a transit event, and then another one, another one, another one, and stack all that data together. And we may need to look at like 10 transits or 50 transits for the planets of prime interest, and that may be quite challenging. I just want to check how much time I have here. We said 45 minutes, I think. Like maybe 20 minutes, yeah, 10 or 20 minutes, okay. So I just want to tell you one more funny story. So what I did with this was, this is a kind of interesting thing because we're so gung-ho about finding signs of life, and the way we're going to do that is we're going to look for biosignature gases in the atmosphere, gases that don't belong, that could be ascribed to life. Now here on Earth, we have oxygen. Our atmosphere is filled to 20% by volume of oxygen, 20%. Without life, without plants and photosynthetic bacteria, we would have essentially zero oxygen, essentially zero. So we're hoping that there is life on another planet, and we're not too far away, and that they can build a space telescope. Maybe it's the test James Webb combination, and maybe they can see that we have oxygen in our atmosphere, and maybe they can ascribe it to life. Oxygen is a very reactive gas. Its lifetime is short. It should not be there in significant quantities unless it's being continually produced. I mean, there's always false positives, which we think we have a handle on. So we want to do that. And so one question is we come up with, well, do you think we could find life with this system? So I actually, for a colleague's birthday party, I did a thing, I called it the revised Drake equation. And for you, if you know what the Drake equation is, you'll get this. If you don't know, you won't totally understand. But the Drake equation was, what is the chance that there's intelligent life in the universe? And Drake essentially took 6 terms, and they were like what's the rate of star formation, anyway. But I took that and said, we can do a real thing now, and we can write down 6 terms and say, what is the chance we'll find life with this test James Webb combination? We have to know how many stars we can search, what's the fraction of planets in the habitable zone of small stars. We know that actually from Kepler. We know what that number is. What fraction of these stars are going to be too variable, so we can't do observations. And so we have sort of a series of terms that we can quantify. But then the other 3 terms, just like the original Drake equation, we can't quantify. Like, is there life around every planet that is in the habitable zone? We don't know. And then we would say, well, does all of that life make a signature, output a gas, essentially, a byproduct gas that is observable? Like in our case, as humans, we're breathing out carbon dioxide. Not helpful. We already have carbon dioxide in our atmosphere. So, you can sort of put that together. And it's just really for fun, but actually people ended up really liking this equation. I have to do it right, because really each term has to be a probability. I can't just make a number from 0 to 1 and then multiply. So I've got to kind of get back to this. But ultimately, if everything worked out in our favor, and honestly, this is like winning the lottery 5 times, but if we know the problem, we know how many planets are in the habitable zone of the small stars, but if every one of those had life and half of those produced a spectroscopic signature we could detect, we actually have a shot at finding a sign of life, in the next decade with this system. It's kind of cool to at least think there's some hope. We're going to do it anyway, right? It's not just the life we're looking for. Tests will find literally thousands of planets. We're going to have a field day with this. But I think now I get to get into the favorite part of my talk. And that's because since the test thing won't work, we have to, and it only works for big Earths around small stars. The question is, how do we find the true Earth twin? How do we go out there and find our true Earth twin? And honestly, this is what I'm spending literally all my time on. I should probably be at home now working on my interim report for this concept study that I'm chairing right now that's NASA sponsored. I'm going to tell you about it now. So our problem with Earth is not so much that an Earth would be so faint. It's about as faint as the faintest galaxies the Hubble Space Telescope has ever observed. The problem is that our Earth, it's right next to a bright, massive, big star. And in the case of our Earth and Sun, in reflected light at visible wavelengths, our Earth is 10 billion times fainter than our Sun. Think about that for a second. We would need to go up there in space and get away from the blurring effects of Earth's atmosphere and block out the starlight to 1.1 part in 10 billion. And think about the field you work in for now, whatever it is, and it might not work if it's math, but for any experimental type of theory, you have to go out to 10 decimal places. How many fields have measurements? I mean, there are some, so those of you coming to dinner, I hope you'll think of one to tell me. I need some examples. But 10 decimal places or more, you probably need 11. It's just insane, right? How are we going to do this? Well, people have been working on this in exoplanets for probably 10 or 15 years now, but we finally got to the point where technology is maturing. We went in this building. We now know there are small planets are everywhere, and we actually have a shot at trying to do this. So there are many ways to block out the starlight. They all involve, the way that we're doing this, there's several ways to do it. One of the ways that we're studying is the star shade. The star shade is a very specially shaped screen, as shown you there. I'm going to tell you why it's specially shaped in a moment. And it would block out the light of the star so that only the planet light reaches the telescope. It's analogous to just taking your hand and blocking out the starlight, okay? Or the light, rather, but it has to be a very special shape and aligned very precisely. Now this, I'm trying to say it with a straight face because usually the audience starts to smile. When I say this screen here is about tens of meters in diameter, and it has to fly tens of thousands of kilometers from the telescope. It's actually it's not the hardest problem, is the formation of flying. And then you'll see the planet directly. This is not to scale, so this is tens of thousands. This telescope could be anywhere from 1 meter to 10 meters. We think we can do this with a 1 or 2 meter telescope. And the stars, of course, are very far away. So why does it have to be this special shape? Oh, okay, this just said, I forgot, I told you, let's see, a specially shaped disk is positioned between the space telescope and the target star to block the light from the star. So what happens is diffracted light is a real problem. And if we could have a circular, perfect telescope in space and look at a point source star, what you would actually see is not a point source star. You'd actually see, if this was your circular telescope, you'd see this pattern. This is on a log scale, but it's just to show you. You see this airy ring pattern, okay? It's equivalent, it's analogous to dropping a pebble in a pond. You get waves. Light is a wave. it can act as a wave, and it'll actually the wave will go around your telescope, making essentially waves on your image. And that's just like dropping a pebble in a pond where you get ripples. Now what people want to do in optics is have a clever shape. So we can imagine for a second that that's our special screen in space, or it could be the mirror of your telescope, or it could be like a stop somewhere in your optical path. Now imagine you have this shape. And we can't do this, I don't think anyone here can do this intuitively, okay? You'd have to work out the math. But this is, you'd actually get an image like this, where all of the diffracted light is sent to the edges, and we can do ones without this central spot. But we throw the light to the edges, and all you would see is the planet light. And this is, the analogy would be if you could drop a pebble in a pond, and instead of getting those ripples, you actually get a perfectly smooth pond to 1 part in 10 billion. Only at the outer edges, it's like this very crazy chaotic rippling. And that's what the concept is. It's using light to your advantage now. Now to get that to be 1 part in 10 to the 10, okay, that's hard. There are certain tolerances that these have to be made to. The width has to be maintained to, it has to be manufactured to tens of microns. So each of these petals could be 7 meters in length and maybe a meter, maybe like that wide, And they have to be deployed to a certain position. You know, they're sort of in-plane, out-of-plane, has to be a certain way. When it's aligned, it's got to be aligned tens of thousands of kilometers to maybe a few hundred kilometers. It's not too hard. Laterally, it has to just be positioned to about a meter. So we're not talking about picometers here or nanometers. You know, these are numbers that are not too hard to handle, actually. But that's the basic concept of the star shade. And okay, I'm going to show you 2 movies now. And this one's an animation showing you how the star shade and a small telescope could launch together. And the petals would unfurl from their stowed position. And there's a central truss, which will expand, and the petals will snap into place. The central truss actually comes from large radio deployables. It has heritage from that. This truss is about 20 meters in length, 28 petals in our design with about 7-meter length. And then the star shade and telescope would separate from each other, getting to that tens of thousands of kilometers separation, and block out the starlight so you can see the planets directly. This artist made a Jupiter and Earth system. That's sort of a very generic concept of what this particular thing is trying to do. This was made by JPL. So I'm actually even more pleased to show you the next video, the next movie, which is, it's going to show you the 2 stages of the deployment. Now it's showing you, this is real time, showing you 4 prototype petals that were, there's another version made with more flight-like materials. These ribs actually snap up passively. This is all passive deployment. So in space, this is exactly what would be happening. It would just be unfolding. And again, the central truss, this is at Northrop Grumman. It's left over from demonstrations for what eventually went to space to be large radio deployables for communication. Now you're seeing the second stage of deployment. You get the people in there for scale. And this is showing you where the central truss expands, pushing the petals into place. And they repeated this whole deployment 25 times to show that it could go to the position required within the tolerances. And people always ask, why are there people here? Should this happen without people? But they're not trying to demonstrate that it happens automatically. They're trying to demonstrate that the same deployed position is reached, each time, to show that in space it would work out. So that's just a total small snippet of the Starshade mission. I'd be happy to answer more questions about that. I have to tell you that I was just at last week I was reporting on this mission to NASA, basically, and in Washington, D.C. And what we did was, I wish I could have brought it today, so I'm going to tell JPL that the next time I do this, I need it here. But what we got to do was bring a prototype petal. And that petal is, think about that for a second. Well, the one we brought was 2/3 scale mechanically, so it was 5.5 meters. So you multiply by about 3.3 to get into feet, so that would be, I guess, 15 or 20 feet. It was so big, we'd have to lay it sideways here, but it was pretty cool. And I was really, if I may just brag for a second, so the 2 first meetings, we were trying to show people what we had done, because once they see it, they won't believe it, and we're here, there's a lot of politics involved, unfortunately, because there's many concepts, and we need to show that this is really happening. But the second, by the time I gave my 3rd talk, it was to a group called the Goddard Memorial Symposium, and it was really cool, because I got to give the opening talk to the NASA administrator himself. And he came over and he loved the prototype petal, because the engineers, it's just like they're kids again. It's so cool to see it. And then all sorts of the associate administrators of NASA were all there, and everyone in the room was from industry, and people just came up and they all wanted their picture taken with the petal. So it was pretty fun to see, professionals just get super excited about a piece of prototype hardware. But honestly, if you could see that prototype petal, you know, it would be like this long. It's just one petal. And so it just gives you a sense of how big it is. But we're just proud to say that we can manufacture it to the precision required. And the deployment tests are all going well. So I think I just have a few more slides here to tell you what are we going to do when we find that Earth. And here's a real picture of Earth. This is one of Earth as seen from Voyager 1 for 4 billion miles. It's just a pale blue dot. That line is actually scattered light in the camera optics. We actually have this thing called zodiacal dust, where our asteroids grind together and they create dust. So we really think if we find another Earth, it will be embedded in some kind of zodiacal dust. So this actually looks like a great image for it. At the end of the day, wait, I just want to see, I think I'm basically almost done here. Okay, I am, but I'll just tell you one more story. This is my last slide, actually. So at the end of the day, we want to try to find signs of life. And this gets me a bit of a problem here, because on our Earth, we have oxygen, as I told you, but did we always have oxygen? Do you think another planet will have life that makes oxygen? I mean, I don't know. I don't want to get out there and have that transiting. I don't want to spend the rest of my life getting the Starship launched and maybe look at 20 or 100 some-like stars and maybe find 5 planets. And if all we can look for is oxygen, what are the chances that, you know, one of those 5 planets is going to have it? So then recently, I embarked on research to try to understand what are all the gases that could be made by life. And, or even not even that, what are all the small molecules that could be both volatile and stable? That means they could be in gas form and they could be stable. And maybe we could have like a list of things that we should look for. And maybe we won't know if they're made by life, but if they appear in such huge quantities, we may have some probabilistic sense of what the probability is that life exists in our galaxy. And so just for my last story, I'll just tell you the story of that. So I'm actually consider myself an astrophysicist. And once you become probably a professor in any field, you start getting like emails from people about their theories. There's so many theories. I don't know if it filters down to students here, but it's just crazy how many people have their own theory about physics. And like we couldn't even look through them even if we had time because they're just too incomprehensible. But sometimes they may be self-consistent, like based on what the person knows, it might be, you know, self-consistent in their thinking. I don't know why so many people want to come up with a new theory, but they did. But the funny thing was, I feel like I came up with my own theory. And I was on the other side, it was like the crank theory. And I had 2 biochemistry friends or colleagues, and we worked very hard together. And we went to essentially a biologist, Jack Shostak. He's actually a Nobel laureate in physiology medicine. He's across the river. He's actually an astrobiologist, so I saw him after I gave a talk. He was at the dinner, and so I said, well, can I come to you with my theory? So I'm now like the crank theorist, and we go march over, and we have this whole theory. I'm going to tell you the theories in a second. And he kind of shot it down right away. But I still think there's kind of something to this, because you know what I discovered? I wanted to go through a list of all small molecules. And the first question was how many of those small molecules are stable and volatile and are produced by life on Earth. And I started to find that like every one was produced by life, like carbon dioxide, you know, ozone even is produced. Even Jack Shostak told me at this dinner that ozone was produced inside some cells for some reason. You know, pick something small, nitrogen. All these things are produced by life. They're all mostly naturally occurring also. And so I went to listen to everything I found and was like, wow. And I learned, you know, usually when you get to be a senior professor, your time for pure research is unfortunately quite limited. But I did take a summer. I learned how to program in Python and how to scrape websites, and I wrote this combinatorics code in my original language, which is C. I took the atoms, the big 6 biochemistry atoms, carbon, nitrogen, oxygen, phosphorus, et cetera, and you know I did up to n equals 10, and what my biochemistry friend had said, that you know you never believe your friends. I didn't believe him. He said I did the approach totally wrong. And then we went to see Jack Shostak. He's like, you did it wrong. Because the way the biologists or the chemists will do it, they'll do everything but hydrogen. And then do the combinatorics. That's how they would do it. And then we have an extra, because you know when you write something down combinatorically, that means I take those elements and I put them together any way possible. Some of them just will be gibberish, like it won't be a real molecule. But they said they would do that, and then when there's like a valence electron free, then they'll fill it up with hydrogen. So it was sort of a different algorithm. So we worked through that. And I feel like out to some small number, all small molecules are produced by life. And certainly in our own atmosphere, all the molecules that are present to 1 part in 10 billion, except for the inert gases like argon, actually are produced by life, as well as being naturally occurring. So I don't know if I'm onto something. There's no real end to this story. It's just the joy of science. I really thought this, we found enough counterexamples, you know, that it couldn't be that all small molecules are produced by life. But there's certainly a lesson here, at least, for the search for life beyond Earth, in terms of atmospheric remote sensing, that really it could be many, many things, many molecules. So this story's not over yet. Maybe some other time I can fill you in once we get, once the summer rolls around and I have time to research again. I'm definitely going to be making progress on this project. But the reality is there are lots of molecules produced by life, hundreds if not thousands of chemicals produced by life here on Earth, and we're just trying to figure out how to recognize a molecule it's in another atmosphere far away that we could attribute to life. So to summarize my talk, is there life out there? I just want you to know that the real search for alien life is going on. We found lots of planets orbiting stars other than the sun. We know that small planets are everywhere. They're extremely common. Our goal now is to find planets around the nearest stars so that we can follow up their atmospheres with new space telescopes. And our search for alien life is not the search for little green people, but it's a search for gases that are produced either by intelligent life or by single-celled bacteria. And I believe that this actually is really within reach. Thank you.
So thank you, Professor Seager, for that really interesting talk. We have time for questions. So if you have questions, please raise your hand.
So suppose this actually happens and the Great Telescope finds oxygen or some other major. What happens then?
The question is what happens? Let's say we find an oxygen. I almost want to put that back to the audience who are, what would you do next? I mean, you can think about that, and that's a good dinner conversation. There's many things we could do. So the astronomer would say, well, now we get to build our next telescope, a bigger one, to confirm the signal, get better signal to noise, to look for more examples, because we don't just want one example. And that's something that will definitely happen. But you know what people really want to do? And this is actually the question that I get asked absolutely most often. It's not, are there habitable planets? That's a common one. It is, can we go there? If we find something like oxygen, what are we going to do next? We're going to build another space telescope? We're going to try to find a way to get a robotic probe to another planet. And actually, I believe that eventually it's the second one. I think once we see interesting things going on, it's not going to be enough just to see it telescopically. And that actually is quite futuristic. We have no idea how to travel fast enough now. People talk about sending out a probe. It could take tens of thousands of years. It's too long, probably. You could send another one later and they could relay back. And then you get into the theory of the Star Trek theory. There was that one episode where they, I'm thinking of like Next Generation here, but there's a spacecraft that's like totally lost because they went out before they were really ready. And like many generations later, they're sophisticated enough to find them and bring them back. So people say, well, why send a probe now? Because you'll be building better, more sophisticated things later. But if you never send one, you may never actually get to the next one. So there's a lot of debates going on about how this would happen, but I believe at some point in the future, that's what the next step will be. Okay, next question. Let's go back there to the second question. Yeah.
Actually, my question is planets were a year is only 10 days. If there are human beings, how would you expect them?
The question is, if we had a planet that was like those small planets inhabited zone of a small star, and if we had humans on those with their year was only 10 days, how would they live? I mean, I don't think they'd have a problem. It would be like, if they have the right temperature and they have energy and they have water, what else do they really need? I don't think the day-night cycle is a problem for them. I think here, us humans on Earth at least, people have a problem if they go to, Alaska or the South Pole, but I think it's fine. I think they would have a way to survive. Next question? They're using the microphone. Yeah.
Thank you very much for your very nice talk. I'm curious to hear what the definition that astrobiologists have of life. I'm motivated to ask this question because on our very planet, on Earth, we're always surprised by the diversity of extremophiles living in seemingly uninhabitable places. So how can we be sure not to set too stringent a definition on life so that we don't miss some forms of life out there?
Right, okay. I'll summarize by saying what is our definition of life and is it sufficient so that we won't miss life elsewhere? So this is one question I get to not answer because I should know what the current definition of life is, but actually I don't know it. And I don't usually worry because in exoplanets, we're not really so much worried about how life is defined, what life is, but we worry about what life does. And so in our case, we're assuming that life metabolizes. So it's the one thing we only care about, that it uses chemicals to store energy, and that eventually through metabolism of chemicals, it will release a gas that will accumulate. So as far as life goes, we're not so worried how it's defined, just what life does. And the bad reason why we don't really pay attention to what the definition of life is because we are going to have so few planets, at least like in our first round, our first iteration of the James Webb or the star shade, we're only going to have a handful of planets to look at. So we're going to look at every planet that's even within anything reasonable. So we're not going to be limited by the definition of life, but rather what nature gives us in terms of how many planets that we can really search for. And so in our case, we just fixate on the fact that life metabolizes, at least we hope some other life will also use chemicals and will give out a gas that will accumulate that we can detect. So I know that's not the answer you were looking for, but I hope it helps in the case that we're not being limited because we're going to have so few targets. We're going to look for whatever is possible in whatever way. And in fact, we won't even really know the surface conditions well enough to even worry about, not discarding a planet because we think it may be the wrong temperature. Yeah.
I was wondering if you get to the point where you can see signs of environmental pollution in the atmospheres of other planets, or signs of perhaps nuclear explosions or radioactive pollution. Could this be a sign of life, but it's no more intelligent than we are?
Okay. Well, so this may be, actually, so in a cool kind of way, you kind of answered the other question up here, is what would we do next? If we had a much more sophisticated, bigger telescope, then we could look for these much harder things to see. So our first generation, we're looking for oxygen or gases that essentially fill the atmosphere. They're 20% by volume, they're global. And we can imagine smaller things like chlorofluorocarbons. Those, to our knowledge, never occur naturally, and they're definitely a sign of life, intelligent or not, depending on how you define it. Some kind of intelligent being that can generate it, or nuclear explosions or radioactivity or light pollution, by sodium lamps, or things like that. We think that, we love thinking about that, but it's way downstream for us. So we can't see that right now, because they're not global gases that, fill the atmosphere in some huge amount, but definitely of interest.
This is also downstream for you, but there's a lot of talk about how wonderful it would be if we could actually do direct imaging for exoplanets. So what are your thoughts on any future improvements in telescope technology for direct imaging?
So the star shade is a form of direct imaging. We have other forms of direct imaging is where we block out the light and see the planet directly. The starlight, see the planet directly. Transits are not considered direct because you see the light shining through the atmosphere. Right now, direct imaging is going strong on the ground. We're doing our next generation. When I say we, I just mean the community. GPI, Gemini Planet Imager, is just come online in the southern hemisphere, an 8-meter telescope, Gemini telescope. And they won't find anything near like solar system planets, not even Jupiter really. They're looking for bright, hot objects that are young and self-luminous, far from the star. Now in terms of direct imaging, I think it will happen. And I have to, of course, because it's what I'm spending all my time on. But right now, so you have to describe this. Right now, in terms of space, there are 3 ongoing studies. I mean, they are just studies in a way, but they're all direct imaging. And that's what NASA hopes to do. Parts of NASA hope to do this. Once the so-called, this is a bit of political talk for astronomers, but once the James Webb Space Telescope launches, there's this funding wedge. They want to do whatever they can to keep that flowing to astrophysics. And so my Starshade committee that I'm chairing, there's also the internal chronograph one, and there's the so-called NRO telescopes, National Reconnaissance Office telescopes, where they're considering internal chronograph for. So there's those 3 options of doing direct imaging. And the chance of one of them happening, the chance of the NRO one happening is pretty high. They're only going to be able to do colors or crude spectra of Jupiter's. But one of those 3, the chance of one of those 3 happening is probably 80 to 90%. That's what we were all in Washington for next week. So I think it's quite high. It's sort of a natural thing. There's like a big snowball rolling and momentum building. Once you've done tests in James Webb, what is the next thing? It has to be direct imaging from space. And now what we're doing is considering smaller, cheaper things. They're all really expensive still, but much easier to do than the previous ones.
So that's all the time that we have for questions for today. So some of you were selected to join us for dinner after the lecture. So if that's the case, you should have gotten the email specifically from me about the dinner. And there are name tags at the back of the room for the dinner invitees, so please pick that up. So that's your ticket to the dinner. And we'll head over as a group in a moment. Otherwise, thank you all for coming, and hope you enjoy the lecture, and let us thank Professor Seager.